So I have a few questions for you they're on stuff that you've gone over after magnetic fields and forces, just a variety of things, mostly quantum kinds of problems. And so I just wanted to start out by saying that in quantum mechanics we notice something, and that's that particles are waves, and that waves are particles. So this is something that you probably already know. You already talk about light waves, and think about light waves as being made up of photons. So photons have a kind of location. You can find out where they are, and yet we've used wave equations to talk about light. So light is both of those things. It turns out other waves also can and are usefully thought of as both of those things. In particular, a standard thing that people do is think of sound waves in solids or liquids. Sound waves are just oscillations of atoms, but it turns out that sound waves come in discrete energy packets, just like photons do, just like light waves. And so sound waves in a solid, there's a name people give to the energy packet of a sound wave in a solid. It's called a phonon. Sounds a lot like photon, but it's an energy packet of sound wave instead of a light wave. So waves come in units. So waves are like particles. They have momentum. The particles have momentum, and they have energy. Similarly, electrons, you probably already know, act like waves. So do atoms. So do protons. As far as we know, so does this pen. But the predictions of a wave equation for this pen are utterly and completely the same as the predictions for particles. So there's just no way to tell whether this pen, no way that we know of, to tell whether this pen is actually moving around like a wave or exactly like a particle. But just because all the particles for whom we expect to be able to tell whether they're waves or particles seem to be both, we would conclude that the pen is both also, just not usefully thought of as a wave usually. If particles are going to be waves, then they have to have a wavelength. So I'm going to start by just writing one equation that'll be on the final. By the way, on the final exam, there will be an equation sheet. The last sheet of the final exam will be an equation sheet. And we will also let you bring a small either sheet or card or something of notes, of your own notes, to the final exam. I have to discuss with the rest of the instructors because we want to have a uniform across the set of 7C classes. So I don't know exactly what we're going to do, but we'll allow you to do something, and I'll probably by the end of the day today we'll have that straightened out. So I'll just tell you on SmartSide what size piece of paper or card or whatever you can bring with your notes, in addition to whatever set of equation sheet you put on at the end. One of the equations will be an equation that tells you something about the wavelength of a particle. So the wavelength of a particle depends on its momentum. P is the momentum. If you remember from 7b, momentum is just the mass times the velocity. And the constant that relates the two is Planck's constant and h. And that'll be on the final two. The constants will all be on the final, whatever constants you need, and whatever numbers you need. So large momenta have small wavelengths. So that's what that equation tells you. If something has a big momentum, it has a small wavelength, which explains something about why this pen doesn't have wave properties that we can see. Its mass, the momentum of something is the mass times the velocity. This pen has not Avogadro's number of atoms, but a big, giant number of atoms. So it has a gigantic mass. And so its momentum is gigantic considered compared to atomic scale particles. So its momentum is gigantic, which means its wavelength is incredibly small. It's so small that you'll never be able to tell that it even has a wavelength, basically. Okay, so I'm going to give you 2 or 3 minutes, maybe 4 minutes, a little bit of time to talk about and think about this first problem. The decision, your answer, as usual, your answer is important, and your explanation is more important. So there's one thing to get it right, and it's another thing to explain it well, and the explanation is going to be the main thing. So in determining how well you did, or how well you understand this physics. Picture to the right shows a bunch of equipotential lines. So these dotted lines or dashed lines are constant potential lines. The potentials are listed here. Here's 2,000. There's 4,000. There's 6,000 volts. Suppose an electron is released from rest at the center of this region, so it's released right here at 4,000 volts. Decide which direction the electron moves. Explain how you decided that. And decide whether the electron's wavelength will get larger, smaller, or something else as time goes on after it's released. So take a few minutes and think about not only how to answer that, but how to explain your answer. This equation for kinetic energy, I think, will also be on the final exam, although I suspect you remember it. I just wanted to point out that you can also write this same equation like that, where P is the momentum. Because if you look at this, P squared is, well, P is mv, so P squared is m squared v squared. And if I divide m squared v squared by m, that just gives me mv squared. So those are the same thing. Those are the kinetic energy. So let's talk about it. I'm assuming you have basically thought about your answer, and I hope thought about what explanation you would use. So let me ask you, what direction does the electron move after it's released from rest? To the right. A lot of people pointing to the right. Anyone think anything other than to the right? Okay, so now the hard part. What's your explanation? It's released from rest. To me, there's kind of two ways of dealing with the question of motion, and one is energy. From 7a, I hope you know that things will move in the direction that lowers their potential energy. But you can also talk about forces. So from 7b, you know that the momentum change will be in the direction of the force, or the acceleration will be in the direction of the force, either way you want to talk about it. So either one. Someone want to tell me an explanation that either uses energy or uses forces. Couple of other equations that have to do with this that will show up on the equation sheet. Yeah. Okay, so our answer is the electric field points to the left. Electron charge is negative, so the electron feels a force to the right. So that is probably, most graders would call that a complete explanation. You know, if I were being picky, I might say, how do you know the electric field points to the left? I don't think most graders would do that, but how do you know the electric field points to the left? Okay, I mean I think that's what a lot of people, I see your quizzes and I see that a lot of people would look at this, draw a whole bunch of positive charges over here, and draw a whole bunch of negative charges on the other side, and draw the electric field between them, and I can't disagree with that. I mean, if there is a bunch of equipotentials that look like this, then there are, somewhere over here on the right, a whole bunch of positive charges. It's the only way to make such a thing. And over here on the left, there are a whole bunch of negative charges. It's the only way to make such a thing. It's the only way to make that kind of constant equipotential. And so if there's a whole bunch of positive charges over here, then the electric field points away from them and toward the negative charge. So that is a kind of complete explanation that I see a lot of people making, of the kind that a lot of people make. In a general sense, you could also say the electric field points toward the direction of decreasing electric potential. The electric field vector, the magnitude depends on the change in potential divided by how far you've gone, so the gradient, but the direction is toward decreasing electric potential. So that's a force kind of argument. You could also have used an energy argument, like from 7a. The potential energy of the electron, if I'm talking about the potential energy of the electron, then I need the charge of the electron, Q sub E. Q sub E is negative. If you go to the right, you find the voltage goes up. So delta V is positive. If you're going to the right, the electric potential is increasing. Sorry. Yeah, delta V, final minus initial. If you go to the right, final might be 6,000 and initial be 4,000. So delta V is positive. You're going up in electric potential. But because this is negative, that means delta PE is negative, so you're going down in potential energy. Going down in potential energy means going up in kinetic energy. So it moves faster and faster to the right. Or you could say, well, we learned in 7a that the forces are always toward lower potential energy. And lower potential energy for an electron is toward higher electric potential because of that negative charge on the electron. So you can use either a 7a or a 7b kind of argument with these ideas that came out of 7c. What about this one? Will the electron's wavelength get larger smaller or something else as time goes on after it's released? So down, smaller. How many say smaller? How many say larger? What does get larger? It's momentum. It goes faster and faster to the right. Because the potential energy is going down, or because there's a force to the right. Either one tells you the momentum is getting bigger and bigger to the right. And if the momentum's getting bigger and bigger, then because the wavelength is inversely dependent on the momentum, the wavelength has to be getting smaller and smaller. So that tells you something about particles. As they move faster and faster, their wavelength gets smaller. Any of you who have anything to do with an electron microscope might know that what I have shown here, thousands of volts. I mean, 1,000 volts sounds big. 6,000 volts sounds big compared to 100 volts that we have in our outlets. But electron microscopes often have voltage ratings of 100,000 volts or more. So what does that do? I mean, 100,000 volts gives electrons a lot of energy, a giant momentum, and so a really small wavelength. And that really small wavelength is useful when you're talking about really small distances, like the distances between atoms. So electrons in an electron microscope, are often very short wavelength particles. So they need gigantic momentums, which means you generally need a gigantic voltage difference to give them those big momentum. Any questions about that one? Helium atom, xenon atom are each trapped in a region of about 10 to the minus 6 meters in size. That's about a micron. That is a micron. Each has the smallest translational kinetic energy that it can have. Decide which of the two particles has the smallest kinetic energy, and then explain your decision. So these ideas come into play somehow. I'm going to draw a picture. It's trapped in a region. So I'm going to draw that region for you. These are just gigantic walls of some kind that trap the particle in this space that's 10 to the minus 6 meters wide. So you put up gigantic walls and you force the particle to sit in that space in between. This particle is, of course, a wave. Particles are waves. Waves are particles. The statement is that they each have the smallest translational kinetic energy that they can have. Kinetic energy, of course, has something to do with mv squared or p squared over m. Smallest kinetic energy tells you something that is useful for answering this question. I'll give you a few minutes to talk about it. I'll give you a hint in case you can't figure out what to do. Saying it has the smallest kinetic energy possible is telling you that that wave has the smallest momentum possible. Saying it has the smallest momentum possible tells you something about its wavelength. If you trap a particle in that space, what are the possible wavelengths? Is one way of thinking of that. So let me ask you, if it has the smallest possible kinetic energy, then it has the smallest possible momentum. If it has the smallest possible momentum, what does that tell you about the wavelength? It's as big as it can get. The biggest possible wavelength. So what's the biggest possible wavelength for a particle that rattles back and forth in a space of 10 to the minus 6 meters? Twice that. One wavelength would look like that, but you know that it's possible to have a standing wave where there's only half a wavelength in that space. If there's only half a wavelength in that space, then the whole wavelength is twice that distance. So that's the longest wavelength you can get. Which particle has that wavelength? So both of them are in the smallest kinetic energy. So they both have the smallest momentum they can have. So they both have the largest wavelength. So they both have that wavelength. That's the largest wavelength you can get. They have the same wavelength because they both have the largest wavelength they can get. So if their wavelengths are the same, then you can look at this equation. If the wavelength is the same, Planck's constant is just a constant. So the momenta or the two particles are the same. They have the same momentum. And so which one has the smaller kinetic energy? The one with the bigger mass. If they have the same momentum, then the one with the bigger mass has a smaller kinetic energy. So that's the kind of, those are the steps that whoever wrote this problem would like you to think through. Each one has the smallest kinetic energy that it can have. Therefore, it has the smallest momentum that it can have, which tells you it has the largest wavelength that it can have. And since it's trapped in this space, the largest wavelength for either of them is the same number, twice that distance. And so they have to have the same momentum, which means the kinetic energy of the one with the largest mass is smaller. Any questions about that one? A lot of steps there. You have to think of them one at a time, especially if you've never seen anything like this. Quite like that. A question quite like this. Here's one that we haven't had a quiz on, so it's at least a possible final exam kind of question. The ends of a circular coil of wire, coil number 1, that's the one on the left here, are hooked to the positive and negative terminals of a power supply, as shown below. Note the hookup and the way the wire is wound on coil 1. Well, different ways of thinking about this. If I look at this, I feel like the power supply has the positive side is hooked up here, the negative side is hooked up there, and it looks like the wire goes around like that. So what it looks like to me if I draw coil 1, it looks to me like the current is going around like that. And to me, that would be, if you look at it from the right-hand side, the current is going around counterclockwise. So if you come over here from 2 and you look back at 1, then you're looking at current going around counterclockwise. So for the rest of the questions, let's pretend that that's correct. I have a feeling, in fact, I'm pretty sure, that whoever wrote this, that first question on the figure, indicate the direction of the current in coil 1 and explain your choice. I think that problem A, if I were grading it, I wouldn't grade problem A. I would look at problem A and use that to think about the answers to the rest of it. Because the answers to the rest of it depend on what you thought about problem A. And the trouble with, or the confusion that can happen is that there are different ways of looking at a coil on a perspective. I could think, I can imagine, in my mind, this looks like it's running counterclockwise if you look at it from the right-hand side. But it's easy in your brain to kind of flip that around so that suddenly it looks like it's running clockwise when you look at it from the right-hand side. So it's just too easy to not quite know the direction. As long as you know that the current is coming out of the positive side and going back into the negative side, as long as that's your explanation, then I would say whatever direction you chose for the current, I'll call right, and I'll use that direction to figure out the answers from then on. But for right here and for all of us right now, let's take the direction of the current to be counterclockwise if you look at it from the right. And then B, C, D, and E, go ahead and try to answer those. All right, so let's talk about first B. Does coil 1 have a magnetic moment? Yes. In fact, every loop of current where there's current going around in a circle has a magnetic moment. Going around a circle, square, whatever. There's always a north pole, there's always a south pole. So there's always a magnetic dipole. Magnetic moment, they should have said magnetic dipole moment, but still, that's all we've talked about. We haven't talked about, I don't know, quadrupole moments and octupole moments and whatever else is possible, the kind of complicated things that are possible. All we've talked about is dipoles, north and south. So, what's the direction? Well, just answering it, I would try to be as clear as possible. I would try to do something like, by right-hand rule, you can figure out the direction of the magnetic field due to this loop. And since I think of this current as being counterclockwise, when viewed from the right, I would say the direction of the magnetic field inside the center of the loop is to the right, so that it comes out here and goes around. It comes in from the left. It goes out to the right, comes back in from the left. Because that's the direction of the magnetic field, we call this side the North Pole and that side the South Pole. The side where the magnetic field is coming out is the North Magnetic Pole. This issue with the Earth notwithstanding, this is the geographic north equals the magnetic south, it turns out, and the geographic south pole of the Earth, McMurdo Station and Antarctica and all that, are the magnetic north pole. If you think about how a compass works, you can figure out why that people might have misunderstood this situation. They took the North Pole of a compass as pointing towards something that they already called the North. They called that geographic north. Okay, it's this way. Look at this. Here's a compass. It always points toward north. I'm going to call that the north end of the compass. But you already know that if this is the compass and this is the Earth, this isn't going to want to be that way. This is going to want to be like that. It's going to want to flip around. It doesn't want to point. This compass wants to point toward the south magnetic pole of the Earth. So you can see how we would confuse that by saying, well, it points that way, and we call that way north, so we'll call that the North Pole, because it points toward the north all the time. Instead, in fact, it points toward the magnetic South Pole. So, given that that's the North Pole and that's the South Pole, the magnetic dipole moment points from south to north. Just like the electric dipole moment, in physics at least, points from the negative sign toward the positive sign. So the magnetic dipole moment points from the south toward the north. So it points to the right. If this current is counterclockwise when viewed from the right. On the drawing, indicate the direction of the magnetic field due to the coil at the center of coil 2. So they wanted you to put a magnetic field here. What's the direction of that? To the right. Be by 1. At the center of 2, the magnetic field due to 1 points to the right. The current in coil 1 has a constant value. So we turned it on 10 years ago. The power supply, plugged it in, turned it on, and for 10 years it's been the same. Is there an induced current in coil 2? No. Why not?
There's no change in magnetic flux.
Because the magnetic flux through here, the magnetic field in the center of this coil has been constant. It's not changing, so the magnetic flux isn't changing. Magnetic flux, by the way, is just the magnetic field times the area of the coil. So the area of this coil times the magnetic, it's basically that. It's really an integration, but basically it depends on the area and it depends on the magnetic field. So I'll say crudely it's an average magnetic field times the area. So the magnetic flux isn't changing, which means there's no induced current. There's only an induced current when the magnetic field changes in a coil. So the magnetic flux through the coil is changing. So power supply is now turned off. Indicate the direction of the induced current in coil 2 due to the power supply being turned off. So it's going to only be an induced current that only happens for a very short time. It'll be dissipated quickly because there's resistance, and resistance will stop the current from flowing. But in the instant that the power supply is turned off, what's the direction of the induced current? So how do you want to talk about that? Let me, you could sketch it, of course. Let me ask it this way. The current originally, when I look from the right, the current in the coil number 1 is counterclockwise. So I'm just going to say that. If I look from the right, what's the direction of the induced current in coil 2 right when I'm turning off coil 1? Counterclockwise around coil 2 or clockwise? Those are the only possibilities. So which is it, is kind of the question. So let me ask you, how many say the induced current in coil 2 is clockwise when you turn off coil 1? How many say counterclockwise when you turn off? Okay, good. Nobody said clockwise, and all of you who answered counterclockwise, and there were a bunch of you. So yeah, there was a magnetic flux to the right through coil 2. When you turn the current off, suddenly that goes away. The induced current in 2 is to try to make up that change. In other words, to bring back that magnetic flux to the right, and that means this had to pick up an induced current that is in the same direction as the original current so that the magnetic field would be in the same direction. It tries to make up for the missing magnetic field that suddenly disappeared from the center by producing its own magnetic field. And if you suddenly turned it on, so you go from no magnetic field anywhere to suddenly having a magnetic field to the right through coil 2, and coil 2 would try to cancel out that magnetic field to the right, so it would try to produce a magnetic field to the left. And so if you suddenly turned it on, the induced current would be the other way. It would be clockwise instead of counterclockwise in order to try to get rid of the change. It always fights. The induced current is always a way of opposing the change in magnetic flux through the coil. Any questions about that? It seemed like most of you got that pretty well. I didn't do these calculations, so I'm kind of hoping that you have time to do some of these for me, or else I'll do them at home and post them when I get there. When I post the questions. This is actually a fairly complicated problem. This is what spectroscopy is all about. It's all about exactly this problem. Imagine you've observed several photons emitted from some excited substance, like in a gas discharge tube. Suppose the wavelengths you observed were as follows. So wavelength is what you measure, generally. You use a diffraction grating, you look at the angle that they're diffracted at, and you can measure, because the diffraction depends, you can measure that angle very accurately. And the angle of diffraction depends on the wavelength. So the wavelength is something you can measure very accurately. So you end up with a bunch of wavelengths accurately measured. They've written it down to 5 decimal places. That's not impossible. You can do that kind of measurement. It's not crazy hard to do. From those wavelengths, you need the frequencies of the light. And the whole point of a spectroscopy experiment is to find out the energies of the photons. Because the energies of the photons, so first question, find the frequencies, so fill in this chart. Second question, find the energies of the photons. And the third question, construct a quantum energy spectrum that could have produced these energies. So that's the whole point of a spectroscopy experiment, to try to get at the energy levels, to use these photons emitted to understand where the energy levels sit. So that's always the idea behind a spectroscopy experiment like this, where you observe photons, where you measure wavelengths, you find frequencies, you find energies. I didn't do the calculations, but what I did do was put in the equations that would be sitting at the end that let you do it. What do you have to remember? You have to remember you're looking at photons, which means light. The velocity of a wave is always the frequency times the wavelength. And for light, the velocity of the light is c. That's the velocity of the light, and that's, well, if they're going to give me that careful accuracy, I think it's 2.99 times 10 to the 8th. Meters per second. I would usually call it 3, but I don't know, somebody's given me a really careful wavelength, so I guess we should try to be more careful. It might be 2.998. Let's write 2.998, in which case 3 starts to look like what you really should call it. And for our purposes, well, really, for our purposes, 3 is fine. If you really want to know the energies that well, for some reason, you can worry about the real number. And then the energies of the photons depend on Planck's constant times the frequency. So once you've found the frequency, you can find the energy of the photon just from Planck's constant. Again, something I don't really know. I think it's 6.63 times 10 to the minus 34, I think. Joule seconds. You can put more digits on it than that, but it's something like that. So, if somebody could calculate somebody start at the beginning and calculate energies and frequencies and energies, and somebody else start at the bottom and calculate frequencies and energies. And because I'll just write them in if you can give them to me. And we'll construct this thing right now. Anyone get any of these yet? Frequency or energy? Nano is 10 to the minus 9 meters. So that's 28 times 10 to the minus 9 meters. And 99 times 10 to the minus 9 meters. And the speed of light is 3 times 10 to the 8th meters per second. And h is 6.63 times 10 to the minus 34. Yeah.
I got a frequency.
All of them? Okay, great. Top one?
And I got 1.05 times the 16th first.
Okay.
Next one I got 3.018 times 10 to the 15th.
Let's call that 3.02 times 10 to the 15th. Okay. And last one?
Also I got 7.55 times 10 to the 15th.
Everybody okay with those? So energies? 10 times 10 to the minus 18th. 15? Also 18. Joules. Makes sense. They're about 3 different. 5.007 6, whatever. They're all good enough for a final exam kind of question. The reason I wanted to look at these, and I wish I had done this before, done the calculations, is that the energy spectrum that you construct, you want to have, I mean, there's going to be a ground state, and then there's going to be at least 2 excited states. There have to be. If you only had 1 excited state, then there would be only 1 kind of light coming out. If you put another excited state up here, then there's those 2 kinds of energy changes, and also this one. And so the question I have, I guess, is, and this works, the sum of 5 and 2 is 7. So I was wondering if whoever set this up, I mean, they gave you these numbers, so maybe they gave you these numbers for a reason. This one, the longest wavelength. Remember, the longest wavelength is the biggest wavelength is the smallest frequency, and so that's the smallest energy photon. You know, I hope, that the energy of the photon emitted, and so this is just conservation of energy. If a photon came out and there was no photon at the beginning, then the photon at the end has to be compensated by a decrease in energy somewhere, and so it's equal to the energy change. Actually, let's do it this way. The energy of the photon emitted plus the energy change of the atom is equal to 0. That's just saying energy is conserved. The energy change of the photon is a positive number because it wasn't there before and now it is. So a photon is emitted, that photon wasn't there, now it shows up, so that's energy added. That's a new energy that went up. So some energy had to go down. The energy of the atom had to go down if a photon is emitted. So that's a conservation of energy kind of statement. Whenever an energy goes down like this, energy comes out. And it looks like 2 and 5 add up to 7. So let me draw it this way. Here's this one right here is 7. Well, if I call this energy 0, then that energy is 7.10 times 10 to the minus 18 joules, because that's the highest energy photon emitted, so that's the biggest jump in energy. The drop from this high energy state to the low energy state. If this one is 7, if the low energy state I call 0, and the high energy I call 7 times 10 to the minus 18, then you'll see that that's energy change is just that photon coming out. And the thing I was interested in was the next two, and they're 5 and 2. So I'm going to call this one 5 times 10 to the minus 18 joules. So this one's 0. This one's 5 times 10 to the minus 18. That one's 7 times 10 to the minus 18. If you go all the way from the top to the bottom, that emits this high energy photon here. Shortest wavelength is highest energy. If you go from all the way to the top to the second one, that's this 2 times 10 to the minus 18, because you go from 7 down to 5. So the change in the energy of the atom is negative 2. And so the photon emitted has to be positive 2 to conserve energy. And if you go from the second one down to the bottom one, that's 5 down to 0. So the change in the energy is negative 5 times 10 to the minus 18th. And so the photon emitted energy is positive 5 times 10 to the minus 18th, and that's this one. And so with 3 energy levels, you can do those 3 things. So that's what it was asking you to do. Thanks for the calculation.